This video lecture covers relational algebra and very specifically how to extend relational algebra to allow for functions, aggregate operations, group by, and such. The major source of material for this is the textbook, section 6.1.4, well, more precisely the 6th edition of the textbook. Unfortunately, in the 7th edition, that material is removed, so you would need to find a prior version than the current version. Codd's 1970 paper is the basis for all of relational algebra. Other background material, of course, includes any material on set theory. Okay, and the cross-reference for this is SQL, data manipulation language, of course. The lecture is broken down into 4 sections. First of all, we'll look at the non-aggregate functions, the application of non-aggregate functions to relational algebra. Then we'll consider how to add aggregate functions in relational algebra, and we'll finish up with dealing with group by operations and order by operations, sorting. Applying non-aggregate functions. So first, let us consider the select operator. The select operator applies a propositional expression of comparisons between relational attributes. Actually, that's not quite true. If you want a pure select operator, you can have select a equals 6, and instead of saying I want to allow things like a equals 6 or b equals 5, you can say, wait a minute, no, I'm not allowing those operators because relational algebra itself allows propositional collectives and repeated operations, so you can simply have select like this in order to achieve that. Okay, so either is equivalent, but broadly speaking, it is considered that they are relational attributes, comparisons between relational attributes and propositional connectives thereof. So if we have things like find patients that are more than 6 years old and they're fat because their waist size is bigger than their height, okay, I guess that would be ridiculously fat, just a random example. You would have select age greater than 6 and height is less than weight size. So this is standard RA. Okay. Now, we can extend this by allowing functions over attributes. So, for example, find all employees with a first name that has more than 4 characters. Well, first name is an attribute of employees. Okay. Char_len is a function. Now, generally speaking, you will write function names and it can be assumed what the function name is by any reasonable person reading your text, or in this particular case, these are standard functions within SQL. Okay, so we have application of a function to an attribute and then the comparison operator. So this is a fairly straightforward approach. Similarly, we could apply them to the projection operation. So the projection operation normally just takes attributes from tuples and limits it to those tuples. So give me the name and department name of instructors. So instead of having their ID and their salary, we're simply reducing it to that. How can we extend this? Well, let's consider information that we don't have. Again, we'll use the char_len function because it's a convenient one. What if I wanted to know what the length of text is that is done by reviewers rather than what the actual review information is? Now, in this particular case, the name of the user is not in the review table. It is the user ID that's in the review table, and so there's a join operation between review and user on the user ID, and then we pull out with projection the name, which is normal, and we apply the function char_len to the text. So those are both fairly straightforward, and you can imagine more or less any simple function you like applying to attributes or combinations of attributes. One other thing I should mention is, if you recall SQL subqueries, there's no reason why you can't have subqueries within your operation. So you could have select, imagine we're having a scalar subquery, A equals, and then some RA subquery. Whoops. An RA subquery, SQ. Or you can have project, and suppose you wanted some average salary, and we haven't shown how to do this, but salary divided by an RA query that gives the average salary in order to figure out whether or not what the ratio of this person's salary is to the average salary. So subqueries can also be placed in here. Okay, continuing. How do we deal with, so these are non-aggregate functions, okay? So continuing, we want to say, how do we deal with aggregate functions, okay? Now the first method is not to do anything special, but simply to apply standard set theory. Relational algebra extends set theory. It doesn't remove any set theory capability. It simply adds operators. So we can use any operator that's already within set theory. And two operators in particular come to mind. The cardinality operator, so cardinality of a set is the number of elements in a set. Okay, if you recall that from set theory. Okay, so if I want to know how many instructors are in physics, select department name equals physics instructor. That will give me a set of tuples where the instructors are in physics. So if we have all of our instructors, and we have an ID and a name and whatever else, and we have 1, 2, 3 Einstein. Okay, and I guess we have department, and he's in physics, and we have 4, 5, 6, and Mozart. He is, of course, in music. So that select operation will produce 1, 2, 3 Einstein, EIN, and physics, and whoever else, 7, 8, and 9, I guess Niels Bohr is in physics, etc. So we'd have a relation of instructors, all of whom are in physics, which I've shown that as a table. In practice, it's Einstein's tuple and Bohr's tuple and so on. So when we take the cardinality of this just gives us a number which is however many elements are in that set, which in this particular case would be the number of instructors in the physics department. What if we wanted to compute the total payroll in physics? Well, let's select the department name equal to physics from instructor. So this gives us all of the physics instructors. Now let's just pull the single column out of that salary. So we wind up with, technically, an array, a set of salaries. Okay. Someone's very well paid, someone's not very well paid, etc. And we simply do a summation over that. Now, if you're a set theorist, you just say, okay, we're just going to say sum over that. And since these are tuples where each tuple contains a single item, then it is understood that that is simply the addition of these numbers. 123 plus 452 plus 12 plus whatever. Okay. If you really want to, you can spell it out exactly. Okay, so you could say summation x is an element of, let's get this right. Summation over the set x, where x as a tuple is in whatever that set is. Okay, This doesn't particularly add value. Any reputable set person will just understand that this is a summation over the contents of the column. So this notation is perfectly acceptable. This then, of course, leads to what's the average salary in physics? Well, it's just the sum of salaries divided by the number of instructors, and that will give us the average. By the way, don't forget that. I've had examples on exams in which it is necessary to compute an average, but in computing the average, it's actually important to do a summation and a division rather than use the average operation because of how the actual application works. I'll have some examples on the resources section. I'll have some examples on the resources section to show you that in a while. Okay, what about max and min? Well, max and min don't even need aggregate operations. They can simply be computed using standard relational algebra. And I showed you this in the previous lecture on relational algebra, but just to review it. And notice that I'm going to make use of these temporary variables because it does substantially simplify it. First of all, let's identify physics instructors. Then we will do physics instructor join itself. Well, we have to rename it, that's important. But we'll join it with that, and we'll join it on the condition that the T relation, the renamed physics instructors where they're T's, have a salary that is greater than this salary, which means the only items in this not min relation are items in which there is a salary that is less than the T salary. So none of these salaries in here are minimum salaries. We can then do set subtraction. So let's take our physics instructors, we'll pull out the ID and salary, and we'll get rid of the min instructors. So this gives us the ID and salary of the lowest salary in physics. So we don't need to do that. Okay. There is a different way of doing it. Is it better? No. Is it worse? No, it's different. Okay, there is this operator, G. Some people call it calligraphic G. I'll just call it G. The G operator takes an aggregating function and applies it to a specified attribute on a relation. So we say G min salary, take the aggregating function min, apply it to the attribute salary, and we will do so for physics instructors. Okay? We could do average salary either by doing G sum salary divided by G count of instructor IDs, but we may as well simply apply average as an aggregating function to salary. Okay, there's an important aside here. The textbook, or at least version 6 of the textbook that included this material, used the operator G. Other textbooks use the operator F, which is presumably for function. And some other places I have also seen the operator A, which is for aggregation. So do not assume that this is standard terminology. And I don't say it's not non-standard because of some standard terminology I'm not teaching you. There is no standard terminology, okay? So you may come across different usage of this, okay? This isn't actually as bad as the case of sorting. There is at least, it's well defined. The semantics of this operator are well defined. Okay, multisets. These are sometimes also referred to as bags. Okay. A set has no duplicates. A multiset, or a bag, can contain duplicates. It doesn't have to contain duplicates, but it can. Now, implicit in both G or the non-RA set theory operators is duplicate removal or non-removal. Now, in the set theory approach, by default, they're removed, okay, because it's set theory, not multi-set theory. So, what if we needed to modify operators to specify multi-sets? Let's go back briefly, to look at this one. What would happen if two faculty members had the same salary? Now, I'll admit the probability of that is low, but there's certainly cases where there are things that would be identical, okay? But in this particular case, we'll just say the probability of this is not 0. Now, if two faculty members had the same salary, when we do the project salary operation, let's say the salaries are 123 and 223 and 223 and 105. We want the summation of all four of those, but if we use standard relational algebra with project, it will only produce 3 of those, because it will reject 223 as a duplicate, and then it will add the 3 of them and divide by 3, and we will get the incorrect answer. So there needs to be a notational difference that says we want to treat this as a multi-set. Now, I should point out this is primarily occurring with the project operator. It is not exclusively occurring with the project operator, though. Okay, there are cases, for example, in Cartesian product where you will get duplicates and you want to keep them, etc. But it's frequently the case that you do not want to keep the duplicates and you're happy to let them disappear. So the particular notation that I use is if I want a multi-set version of an operator, I simply annotate it with a superscript M to indicate that it's a multi-set operation. So in this particular case, cardinality here is fine. Select instructors whose department name is physics. By definition, this is going to be the correct number. There's going to be no duplicates to worry about. In this particular case, it is possible there are duplicates on salary that we wish to capture, so we need that to be a multi-set. Summation is simply a summation operation. It's just going to add everything, so that's not a problem. And this is identical to this. There are going to be no duplicates. So, all we have to do is identify which operators need to be a multi-set. If, for example, it was cardinality, just put an uppercase M. If, for some reason, and I cannot imagine why, we wanted, actually I can imagine why, if we wanted to select on a multi-set, possibly we had project that was a multi-set. So this produced a multi-set, and this, we don't want to throw away the duplicates. Now, I have a hard time imagining that actually being necessary, but for the sake of argument, we'll assume it's possible. Okay, so any operator, a little superscript M would nicely identify it. This is non-standard terminology because, well, all extended relational algebra is non-standard terminology. However, although it is non-standard, it does have solid semantics. There is nothing, the semantics behind these operations would be extremely clear. Okay, so well-defined operations. Now, G, by contrast, does the exact opposite of set theory. Set theory says let's automatically assume there's no duplicates. The G aggregation operation automatically assumes there are duplicates, and it says let's keep them. Okay, if you want to do aggregation with duplicates removed, dash distinct needs to be added to the function name. What's an example of this? Well, how many departments have at least one instructor? So, let's select department name. Let's aggregate over department name and count them, but only count them distinctly. So, For example, let's go up here. We have an instructor relation. We've got Einstein, and he's in physics. And we've got Bohr, he's in physics. And we've got Mozart in music. So, if we're counting distinct department names, we'll count that. This is a duplicate, so we'll ignore it. We'll count this, so there's one music, etc. So this will count each distinct department, okay? Now, many people think G is much nicer than doing the standard set theory operations. This says you're wrong, because literally we just select department name from instructor and count them. So don't need to specify distinct. So this is an example where the standard set theory approach is actually shorter and cleaner. Okay? Anyway, those are two approaches. Okay. What about group by? Okay. Bad news and good news. The bad news is there is no simple method for creating aggregation groups with set theory operators alone. It's possible, it's very messy, we're going to skip it. So that's the good news. The standard approach insofar as there is a G or an F or an A function, the standard approach is to have a subscript prefix to specify the grouping. So if you recall in SQL grouping, we have something like select, let's say we want the number of instructions by department, dept name, comma, count, ID from instructor, group by dept name. Now, it's not particularly pleasant, but that and that basically have to be identical. They don't quite have to be identical. There are different ways to do it, but they more or less have to be identical, and so things are specified twice unnecessarily. Well, in the group by operator, we don't need to specify them twice. We simply have department name is what we're going to group by, and we're simply going to count the IDs. So this will automatically count, and we would get things like music 3 and physics 47 and whatever else. Okay, so we would get the department name and the count. Okay, so this prefix for grouping. Okay, and if we want multiple groupings, we'd have something, comma, something, comma, something, G, and then whatever aggregation operations. And in principle, you can do more than one aggregation operation, but these are messy. Okay, it's certainly for this course, single aggregation operations are most of what you need. Okay, grouping by multiple things, that does happen and can happen. A good example would be, for example, city, comma, province. Suppose you wanted to keep track of, COVID infections. You wanted to count COVID infections ordered by city and province rather than just by province. Okay. One side note, how many instructors are in each department? This is actually slightly incorrect because it omits any departments with 0 instructors. I will leave it up to you to think about how you would do the relational algebra to fix that. Okay. Sorting. Sorting is expensive. Sets and multisets are by definition unsorted. You shouldn't think of unsorted as bad. You should think of unsorted as flexible. Okay? The database is going to do whatever it thinks is best in order to keep track of the data. Okay? Sorting is expensive. There are only 2 cases in which it should be used in a database and only 1 in which you should be using it in any query or relational algebra. The final stage of a report. For example, what are the names and salaries of professors ordered highest to lowest? Okay, it's the last thing you do in your report. It is fair to say that sorting does occur implicitly within databases for specific algorithms, because there may be algorithms in which sorting data can be more efficient for producing the output. Okay, there is, for example, a join method called the sort merge join operation in which data is sorted. But you never actually specify that in the relational algebra. In your relational algebra, you would simply have a join operation with the condition on which you're joining it, and the database optimizer is going to say, oh, a sort merge join is useful. So this is the only condition under which you're doing sorting, or should be. Okay, so what are the names and salaries of physics profs ordered highest to lowest? I use this simple terminology, and I simply have sort down arrow or sort up arrow if I'm going to sort in an ascending order, and then the attributes on which it is going to be sorted. So, whoops, there should be a closing parenthesis there. Physics instructors, sort them by salary, descending order. Okay, one point here, some people have even already asked about this. There is no consistent terminology on this. There is something that you may find called tau. The problem with tau is it's not a well-defined operator. It doesn't have precisely defined semantics. In particular, its sort order is not specified. If you read the material that there is out there on tau, it typically says most significant first. The problem with that is most significant is not a well-defined term. Worse, it doesn't specify the sort order other than this possible most significant, which means it's not clear how to get the reverse of the sort order. So if you're going to use something like tau, please make clear what the sort order is that you're using, because that's rather important. In general, as I said, just specifying your own terminology is fairly straightforward. Okay, limit and the abuse of sorting. Okay, it is all too frequently the case that beginning database programmers are going to use sort combined with limit to achieve some query, such as what are the top 3 or bottom 3 of something. So, who are the top 3 paid physics instructors? Let's select star from instructor where department equals physics. Order by salary descending limit 3. This is bad. This is evil. Why? Because sort is expensive. Okay. You may be used to programming in languages in which you write statements and you think, okay, I write a statement, it should take a certain amount of time. The problem with SQL is you can write a statement that can take a very long amount of time to do. And so it is very, very important that you understand how long the execution time will be for your statements that you write. And things like sorting usually take a long time. Now, there's nothing inherently wrong with things that take a long time if they need to take a long time. But this doesn't need to take a long time because it can be done much more efficiently. Identify your top instructor, that's linear time. Remove that instructor from the set, that's linear time. Repeat that twice more. Those are all linear time operations. So this is much more efficient. Okay? If you want to look at it, let's imagine we're looking at the second smallest or the second largest. Well, if we did it in standard relational algebra, we might imagine doing something like this, okay? If you remember, we created the physics instructor, and then we created the not min which is physics instructors who didn't have a minimum salary, well, then we just add this extra one in here that says, let's identify who the instructors are who are not the second lowest salary. So we will join these two together and pull out the ones where T salary is greater than not min salary, which will mean they're not the second smallest salary, and this then will pull out the second smallest salary. Okay. Join is probably not cheaper than sort. Agreed. So that's not really a good solution. But we can use our G operator. Let's select the physics instructor. We can pull out the minimum salary. Okay, so select salary equals G min salary from physics. Whoops. This should have a phys inst here. Yeah, let me write it over here. Select, just a sec, let me make sure I get this completely correct. Yep. Salary equals G min salary from phys inst. Okay. That's our selection operation. What are we selecting it from? Okay, I need to move this over. So select salary equals G min salary from phys inst. Phys inst. So we're taking the physics instructors and we are selecting from the physics instructors the one whose salary is the minimum salary. Okay. That gives us the minimum salary person. Not min salary is physics instructors minus the min salary physics instructor, which means we then say remove or select the physics instructor whose salary is the min salary in the not min selection. So if you think about it, we have the salaries. Imagine they were sorted highest to lowest. Here's the lowest of physics instructors. Okay. This is not min, and so we select the lowest in that one, and that's this, which is the second lowest physics instructor. So this should be linear time, this should be linear time, this should be linear time, and this should be linear time. The operations should, in the case of a physics department, fine, it's not going to make much difference because there's maybe 50 instructors. But imagine you're trying to find something in a table that's several million columns, several million rows, rather than 50 rows. Sorting several million rows is expensive. So there's a reason why I'm doing that. Anyway, that concludes the lecture on extending relational algebra to deal with the additional issues. I hope you find that helpful.